Turning tools should operate within specific parameter ranges, and we will discuss them here. First, some definitions. Spindle RPM. RPM stands for revolutions per minute. So spindle RPM refers to how many revolutions the lathe spindle is making in 1 minute. In general, when the RPM is higher, the surface finish is better, but on the other hand, higher RPM results in tool wear and possible vibration. In a manual lathe, the operator sets the RPM to a specific value using spindle RPM adjusting handles. Now, cutting speed. Cutting speed is the relative velocity between the tool and the workpiece surface and is represented by meters per minute or feet per minute, depending on the units being used. This parameter may seem abstract, but it is very important in CNC lathe operations. There is a relationship between cutting speed and RPM, which is defined by a formula. Here, you can see two formulas, one for calculating cutting speed in millimeters and the other in inches. As I mentioned, in manual lathes, operators set the RPM, but in CNC lathes, most of the time, a programmer defines the cutting speed instead of the RPM. For example, here you have a sample G-code line. By the way, G-code is the language used to program CNC machines. This sample G-code starts with G96. In most CNC machines, G96 means that the cutting speed is constant, and it takes the number after S as the cutting speed. If we had G97 instead of G96, then the number after S would represent the RPM. Here we have constant cutting speed set at 300. M03 means the spindle will rotate clockwise. Since constant cutting speed, when the diameter where the tool contacts the workpiece decreases, the CNC machine increases spindle RPM, and when the diameter increases, it decreases the RPM. This way, the cutting speed stays constant, resulting in a uniform surface finish for both small and large diameters. Like RPM, if the cutting speed is higher, the surface finish is better, but this might result in excessive tool wear. Feed is the speed of tool movement, and in lathe operations, it is defined as the distance the tool moves per revolution of the spindle. Therefore, in lathe CNC, G95 is used, which means feet is defined as millimeters or inches per revolution. On the other hand, in milling, G94 is usually used, which means feet is defined in millimeters or inches per minute. In this sample G-code line, we have G95, which means feed is defined in millimeter inches per revolution. G01 is a CNC command that makes the machine move to a coordinate at a defined feed rate. X and Z define the coordinates of the endpoint, and F defines the value of the feed. A higher feed rate can result in shorter machining time or smaller machining chips, but an excessive feed rate can cause insert breakage, high machining forces, and vibration. The cutting depth, or depth of cut, which is usually shown in catalogs by AP, is the difference between the uncut and cut radius of the workpiece. A higher depth of cut can shorten machining time, but it can also increase machining forces and vibration. RPM, cutting speed, feed, and depth of cut are the main cutting data that you will define in a CNC program. To find out what to set for each parameter, you can consult the insert manufacturer's catalog or look at the back of an insert box for recommendations. For example, here you can see a picture of the back of an insert box. CCMT 06002 is the insert code in millimeters, and CCMT 21.5.5 is the insert code in inches. Then there are some recommendations for P and M groups of materials. P stands for steel and M stands for stainless steel. Now you can see the recommended ranges for F, which means feed, and VC, which means cutting speed. It's better to start with the middle value of the range as an initial try and then adjust according to your fixture, machine condition, vibration, and other factors. At this point, I want to talk about material groups again. You can see on the insert box picture that there are 6 groups of materials. P stands for steel, represented by blue color. K stands for cast iron, represented by red color. M for stainless steel, represented by yellow color. N for aluminum, represented by green color. S for heat-resistant alloys such as Inconel and titanium alloys, and finally H for hardened steels. Also, you can see two circles below P and M, indicating that this insert is suitable for both steel and stainless steel materials.